All right, hello. It's time for LeetCode Weekly Contest 197. We are two away, or three away, I guess, from Contest 200. Let's go. Hope this one goes well. Okay, hello. I'm now wearing a different shirt because it's what it's Friday and it's almost 1 week after the contest. So sorry about that. This video is just really late, almost a week late. Actually, it's almost certainly going to be a week late because I don't know if I'm going to be able to finish this today. Okay, so yeah, this contest was a pretty high quality contest, I think. And that's not just because I got top 200, That doesn't happen very often, but it's not just because of that. I think the problems were pretty high quality as well. Unlike the last contest, number 4, not a good problem. But these problems were pretty good. I still managed to solve all of them, even though I got a bad finish time. Uh, yeah, I think it was because it was hard, and I solved all of them. I managed to get a higher rank. So let's go over each of the problems and their solutions. Problem 1, water bottles. Given num bottles, full water bottles, you can exchange num exchange empty water bottles for one full water bottle. The operation of drinking a full water bottle turns it into an empty bottle. Return the maximum number of water bottles you can drink. So this is a pretty easy problem to solve, I guess, but you need to keep track of variables. So what I did was I kept two variables, a total and an empty. Total just counts how many bottles you can drink as you go, and that's what you return at the end. Oh, also, I should make this larger so it's easier to read. Okay, so total just counts how many you've drank so far, and empty counts how many empty bottles you have at the beginning. No, sorry, it counts how many empty bottles you have right now. So total starts at num bottles because you can drink all of them. Empty also starts at num bottles because once you drink all of them, you have num bottles empty bottles. Okay, while you still have enough empty bottles to exchange, you can exchange your empty bottles for new bottles by just taking the floor of dividing your empty by the number you can exchange for one extra. So that's the number of new full bottles you can have. And then we need to subtract that from empty, obviously. And then we add the number of new full bottles we have to total. And then once we drink all of those, we have the number of new bottles added to our total. And then once we drink all of them, we get that added to empty because they're not empty. So at the end, we just return total. And yeah, it's a good way to practice keeping track of variables. Problem 2, number of nodes in the subtree with the same label. Given a tree consisting of n nodes numbered from 0 to n-1 and exactly n-1 edges. The root of the tree is the node 0, and each node of the tree has a label, which is a lowercase character given in the string labels. The edges array is given on the form edges I is ai bi, which means that there is an edge between nodes ai and bi in the tree. Return an array of size n, where answer I is the number of nodes in the subtree of the ith node which have the same label as node I. Okay, once you read this problem, you need to have a bit of a think about it, but looking at this diagram really helps. But I guess this part is the next most confusing part. Return an array of size n, where answer I is the number of nodes in the subtree of the ith node which have the same label as node I. Basically, if we're looking at a node which has label A, then we need to find how many nodes in its subtree are also labeled with A. And if it's labeled with B, we find how many nodes in the subtree are labeled with B, and so on. If it's labeled with whatever letter, find how many nodes in the subtree are labeled with that letter. And to do this, we obviously need to have a sort of search. And for this we use depth first search because that takes into account the subtree immediately. Okay, well, yeah, just depth first search because that's the first type of search you think of. First type of search I thought of anyway. So this DFS just does a normal DFS on all the children of the node, but it also returns an array. It accounts how many times each letter occurs in its subtree. And this is going to be an array of length 26, each one representing how many times the letter appears in its subtree. So the first element is how many A's are in its subtree. Second element is how many B's are in its subtree. Third element is how many C's, and so on, until the 26th element is how many Z's are in the subtree. And we need to do this because this information needs to be passed on to its parent. We can't just calculate how many nodes in the subtree have the same letter as the node that we're DFSing on. We need to pass all of the information about all of the letters onto its parent. And this is why we use the array of length 26. And to calculate this array, we just do DFS on all its children, and then we add on the arrays returned from the DFSs on its children together to form the final array. And of course, then we need to increment the element that represents the letter of the node that we're currently working on by 1, because we obviously know there's going to be because this node obviously contributes 1 to A if it contains A, for example. So we always need to set this to 1. And that's how the DFS works. We know the root is 0, so we call DFS on 0, and then the DFS has to do something else as well. Once the DFS is done and you have this entire array which counts the occurrences of each letter in its subtree, then you need to alter the answer, because the answer counts how many occurrences are in a node subtree that have the same letter as the node. But anyway, we can calculate that really easily because that's what the array is. And that's this line over here. And we just start the DFS. That tracks all the answers. And then, just a variation on DFS. And analyzing the time complexity, this is O(n) times 26, because each node needs to process 26 things, but those 26 things are not dependent on its children. So it's only going to be 26n, and n is only 10 to the 5, so we can do it in well under the time constraints. Problem 4. Wait, what? Hold up. Wait a minute, there's 2 hards? Oh, I guess it was, okay, yeah. I think too many people said this was way too difficult, and that's why it got turned into a hard. That's why that's why the contest was so hard. Okay, well, turns out number 3 is actually hard, not a medium. Okay, maximum number of non-overlapping substrings. Given a string S of lowercase letters, you need to find the maximum number of non-empty substrings of S that meet the following conditions. The substrings do not overlap. That is, for any 2 substrings, they don't overlap. Okay. A substring that contains a certain character C must also contain all occurrences of C. Find the maximum number of substrings that meet the above conditions. If there are multiple solutions with the same number of substrings, return the one with minimum total length. It can be shown that there exists a unique solution of minimum total length. Okay, I'm wearing a different shirt again because I felt that my previous explanation was not good enough. It was just way too confusing and too much of a hassle to edit, so I'm going to record the explanation again, except clearer. So this explanation is going to have 2 parts, the overview and then the specifics. The overview is going to tell us our general strategy, and then the specifics is going to tell us how the code exactly works. So we're going to use this example string because we need an example string and we need to be consistent. So it's going to be A, D, E, F, A, D, D, A, C, C. So the overview, we're going to find our 26 possible substrings. So in this example, that's going to be these substrings. We want to find these, but how are we going to find these? Well, we start out with 26 potential candidates, and these are going to be the ones that contain all the A's, all the B's, all the C's, all the D's, and so on. So these are just going to be all the substrings that contain one specific letter. So how do we do that? Well, we find the first and last occurrences of each letter. So our first array is going to look like this. So this first array just tells us the first occurrences of each letter. So this is going to tell us the leftmost bound of our intervals, because if an interval contains all A's, for example, it needs to contain the leftmost occurrence of the A. We also need to find lasts, because that's going to tell us the last occurrence of each letter. So once we know this, we can find the first and last occurrences of each letter. A is going to be 0, 7, C is going to be 8, 9, D is going to be 1, 6, E is going to be 2, 2, F is going to be 3, 3. So once we have these, we have our possible candidates, of course. So we're only going to have these at most 26 potential substrings, but we actually need to do a bit more with these substrings. For example, if we look at the A, okay, never mind. If we look at the interval D, if we look at D, that's going to be the substring 1 through 6. Is this a valid substring? Well, it's actually not, because if we look at it, it contains the letter A, but it does not contain all occurrences of the letter A. So our next step is going to be to expand these potential substrings into valid substrings. And how are we going to do that? Well, okay, we want to find the lowest value of first inside this interval, and we want to find the largest value of last inside this interval. That tells us how far we need to extend to the right and how far we need to extend to the left, because a character inside this substring has another occurrence that's further to the left or further to the right. So if we look at this, first is going to extend all the way to 0 actually, and last is going to extend all the way to 7. So we need to extend it to include this. But then we need to iterate again, because it might include a character when we expanded that we didn't have before. So we need to look at it again. But in this case, we don't actually need to, because the minimum is 0 and the maximum is 7. So we can keep this substring. This is a valid one. So our valid substrings. Okay, so if we look at A, that's going to give us 0 through 7. So, and we don't need to expand that because we look at the largest and smallest values of last and first, and it's already inside there. So C, 8 through 9, that works as well. D, 1 through 6. We saw that didn't work, so we need to expand it to 0 through 7. So that's AA. We already included that, but we're going to use a set, so duplication doesn't matter. Okay, and then E and F are all going to be valid. Once we have these, we're going to sort these by length. So this one has length 8, this one has length 2, this one has length 1, and this one has length 1. We want to take the shortest substrings first, because that's going to give us larger potential remaining space to find remaining substrings. And we don't ever want to concatenate two of these. So for example, if we have the A's and the C's, we don't want to concatenate them, because if we separated those, that would give us 2 additional ones. And taking 2 substrings is always better than 1, even though they have the same length, right? So this is the greedy algorithm. We sort it by length, and then we take the shortest ones first. But if at any point they conflict, so for example, if we took E and F, and then this 8 through 9 conflicted with that, we can't take it, and then we just have to move on to the 8. But if it doesn't happen, then we can just add it. And yeah, that's the overview. So, part 2, the code. How are we actually going to do this? Well, firsts and lasts is computed pretty simply. That's this bit of code over here. First, we just scan through the entire array, and then we just record first instances. Last, we just scan also forwards, except we take the last possible occurrence of that letter. And this is pretty simple. It doesn't really need much explaining. Oh man, okay? And then we can find these pretty easily, the 26 at most potential substrings. And then the expansion is where segment trees come in. So let's look at this. Segment trees are a good way to solve the range minimum and range maximum query problems. So let's explain that over here. Okay, so range maximum and range minimum. Okay, we're just going to say range minimum query for this. When we're expanding a substring, we need to find the minimum possible value in firsts to expand it to. And if we just do an ON algorithm, that's going to be too slow. We're going to get TLE. So we want to find the minimum value inside firsts. Range minimum query tells us that minimum index. So if we take the range minimum query of 1 through 6, that's going to give us 4. And that's going to give us 4 because it tells us that index 4 is going to have the minimum element. Index 4 is going to have the minimum element inside this range. So 0, 1, 2, 3, 4. This is going to be our answer. It's going to be 4. And this tells us how far back we need to extend. So 4 tells us that the index at 4 is 0. So we expand this all the way back to index 0. Range maximum query helps us by determining how far right we need to extend. So range maximum query tells us the largest element. So once we do that, we need to find the largest element inside here, and that's going to be 7. So we just extend right to include these. And this is how range minimum and range maximum queries work. They don't have to necessarily be the same answer. For example, if this was like a 10, for example, we would just take 5 instead of 4. But yeah. And segment trees are useful because they help us solve the range minimum and range maximum query problems. They are included over here. This is segment tree implementation, and it's pretty complicated. I'm not going to explain that in this video because it's too complicated. I wrote this code earlier though, and that's why I could solve this problem. Once we've expanded these substrings to do this, we can find their length pretty easily just by subtracting the start and the end. And then sorting them is very easy because at most we're going to have 26 possible substrings, and sorting them is just going to take constant time. It doesn't matter. Once we sort them, we need to take them one by one from the lowest length to the highest, and then we need to see if it's usable or not. So what does that mean? Well, we have a toUse set, and this is going to tell us which intervals we're going to actually include in the end. And if at any point our new interval that we're considering overlaps with one of the ones that we're already using, then we can't use it, and we just have to ditch it. So that's over here. And if it is usable, then we just add that to our set. I mean, this should actually be a set, but yeah. And then at the very end, we just convert all these intervals into actual strings, and that's going to solve the problem. I think that was a more clear explanation than the last one I did. Yeah, okay. I'm also going to re-explain this one. Find a value of a mysterious function closest to the target. I'm just going to put my previous explanation here because I don't want to explain it again. Winston was given the above mysterious function func. He has an integer array r and an integer target. He wants to find the values L and R that make the value this minimum possible. Basically, what this function is returning is just the bitwise AND of any range inside this array. We want to minimize the difference of any value of this function to a target value here. Okay, so as we loop through the array, we're going to keep a set of all the possible AND values that we have. And if the largest element in this array has 20 bits, for example, then we're going to have at most 20 n possible values of bitwise ANDs. Why is this? Well, consider we're starting at any point over here. Okay, so this is just the array. We're just starting at this point. If we extend our bitwise AND range further to the right, we're only going to get lower and lower values of bitwise ANDs, because when you take a bitwise AND, it can't turn any bit on. It can only turn bits off or keep them the same. So we know that there's going to be a decreasing sequence of bitwise ANDs. And if there's only 20 bits, it's only going to decrease 20 times. And we have n possible starting locations, so it's going to be 20n possible bitwise AND values. And this is linear, so we can actually contain it inside a set. Okay, so our set. As we loop through our array, we're going to keep a set of the possible bitwise ANDs that end at this location. So for example, if our current location is here, this set is going to tell us the values of the bitwise ANDs that stop at this location. So it's going to tell us, oh, there's a bitwise AND over here. For example, this is 20. There's a bitwise AND of this subarray, and this was 40. And there's a bitwise AND of this subarray, and that was 42. So if we have these values in our subarray, when we're looking at our current value over here, well, first we need to add this to our set because we need to make sure that we get all possible starting values. So if this number is 5, for example, we just add 5. But then also, we need to consider that we're continuing these previous subarrays. So we're going to do 42 and 5, 40 and 5, and 20 and 5. That's going to give us a few new values, which I'm not going to compute. And then we just add those to the set, and then we move on. So basically, this set tells us the possible bitwise AND values of all the subarrays that have ended at this current point. And if they ended earlier, well, we don't care because that's already going to be included in the set. And we know that we have gotten all possible starting values because for every possible starting value, we add it to the set. And this is going to give us all complete 20n values. And the code is pretty short. You can just read it. At the end, we just look through all possible values, and then we find the minimum possible difference with our target value. And yeah, that's it. Great. So I hope you enjoyed this explanation. I hope it was clear enough. Please leave feedback in the comments. I'm trying to make these explanations as high quality as possible, but I don't always do the best explanations. So yeah, thanks for watching, and I'll see you later. Goodbye.